outside world equivalent of Lego blocks, okay? So think of Tinkercad as a way to design parts.
Color if you want.
To design parts that, so it's an additive or subtractive methodology, right? So you have a billboard, you take a cube, you set it on your board, you put it at the base, you know, your offset base on the board, and then you can punch a hole in it. You can take a rod, put it in where you want the hole, and then you can subtract that from your cube and you get a hole in your cube, right? Or let's say you want if you want to get really fancy, and you want a cube with rounded corners, then what you have to do is you have to take another cube, you have to take a rod, cut a corner out of the cube, then use that cube to subtract a corner off your other cube. Does that make sense? So you're either making cookie cutters to punch holes or subtract material from something, or you're adding material with another object. Like if you wanted a cube with a rounded top, you could take a sphere, bring it onto your board, cut it in half, right? Subtract half of it off, so you take your sphere, you take a cube, you made them, put them halfway between each other, make the cube deduct the sphere, take the sphere, put it on top of the cube, and add them together, and you got a round top cube, right? Now the sides are still square, but you get the idea, right? So it's
You literally take the tennis ball, cut it in half, and stuck it on top of the square.
on top of the square, and you can and then when you do that, you can make them become one, right? It's not two disparate objects, right? You can melt them together, right? So that's how Tinkercad works. There are some obvious drawbacks to Tinkercad. One of them being, for instance, if you have parts that you need to be pretty precise, like for instance, well, I'm going to show you some stuff in Tinkercad that's very precise, but how I got there is really difficult. I mean, your skills in Tinkercad have to be next level, okay? But like for instance, on like some of your rev parts, they have a hole pattern, right? To make that hole pattern in Tinkercad is no slouch of a task, because all those holes obviously have to be at the right angle and have, you know, perfectly symmetrical circle, and that's a difficult thing to do in Tinkercad. But once you do that, then you have this set of rods that are in that pattern, right? And then you can punch that hole pattern in whatever you want it in. Does that make sense? And so what you would do is you would have that sitting over the side, you copy that, because when you punch the hole into an object, your little hole puncher goes away. And so then, yeah, you don't want to have to rebuild your hole puncher, right? So you use a copy of it to punch your hole. But the real problem is let's say you've got a bracket, and the holes need to be in a particular spot. And putting them relationally inside that bracket is very difficult, because nothing is relational to anything else in Tinkercad. It's all by looking at it, right? You can measure it. There's rulers that you can drop on the board, and you can measure where that hole is. All I'm telling you is it's very difficult and very arduous to do, super painful. So if you need like a test block, super easy in Tinkercad. Drop a 20mm block on there and export the STL. Takes 10 seconds, right? I can show you how to do that in 10 seconds in FreeCAD too, but that is a very easy way to do something really simple, okay? However, the other constraint side of that is if you want to be able to put like CAD drawings of your part into your engineering book, you can't really do that in Tinkercad. You can put a really cool picture of it in there, but you can't put it in there with dimensions and stuff, right? While you can, I guess you could put the dimensions on the board and then take a screenshot of that and put that in your book, but you can't really print it out in like an architectural drawing format like an engineering notebook would actually have it. Does that make sense? So that's Tinkercad. Then the other product I use is called FreeCAD. FreeCAD is a commercial grade product that's free. It runs on Mac and Windows. It's a parametric driven CAD program. Fusion 360 is parametric driven. And now I'll tell you why I don't use Fusion 360. Fusion 360 is a commercial product, and it's designed to have people buy it. They will let you guys as educators, as a mentor educator for all kinds of teams, use it for free. They'll let individuals use it for free. The problem is it's web-based. By that I mean you can't take a drawing, save it on your local hard drive, and share it with somebody. When you share a FreeCAD drawing, a Fusion 360 drawing, you should give them access to your Fusion 360 cloud space, and then they can share it with you. That's how it's designed to work. The problem with that is if tomorrow AutoCAD decides that they don't want you, they don't want to pay for your subscription, they can immediately send you off to your drawings and do all your collateral, all your IP. Well, that sucks, right? So those of us in the DIY community don't really subscribe. There are a lot of people who use Fusion 360, but us hardcore people don't because we don't want to lose. I mean, I've got thousands of hours of CAD drawings of parts, right, that I don't want to lose. And if they decide to start making me pay for my subscriptions, by the way, it's very expensive, I'd lose all my drawings. So FreeCAD, no, that doesn't have that restriction. FreeCAD's been in development for years. I'm now part of that development team because I got really frustrated in version 18. Version now is 19.3 in that. So the game in parametric, does everybody understand what parametric design is?
What is that?
So parametric design is we're going to design, let's say we draw a square in our CAD program, and I'll go through this with you in FreeCAD after lunch, but we're going to draw a cube and we're going to constrain all the things to, you know, a dimension, right? Let's say, so we got a 20 by 30 cube. That's still not constrained in a parametric program, because now I've got to constrain it within an XY coordinate system. So now I've got to constrain it, you know, into XY coordinate system. Now I've got to constrain it within that, but I can constrain it, you know, like this, and center it on the XY coordinate, and now it's fully constrained, right? So, and the reason that's important is because if then I go and change that, everything else that's constrained against that will move with it. So for instance, if I put a hole right here in my part, and I say I want that hole always 5 millimeters from this edge to the middle, right? In Tinkercad, if I make this a 40 millimeter cube, that hole will probably move. It's not going to stay 5 millimeter from the end. Because what's going to happen is when I make that bigger, Tinkercad is going to make it big like this, and then my hole's going to be off, right? It won't be an oval. It could be an oval, yeah, if you didn't do it right. So that's the problem, right? And so in parametric, when I make this 40 millimeters, my hole stays there, right? I don't have to worry about moving. And based on how you design the part, you can manipulate it, and all your holes stay the same size. They stay around. They stay in the spot where you want them to be, right? Relationally to everything else in the drawing.
So you're listening to this
Yeah,
big time, right?
yeah.
And you're like, oh yeah, that's what we want to do. That's,
Yeah.
So we did a class during the summer.
So, to let you know though, I have designed 2 robots for SEC, one in Tinkercad, and another in FreeCAD. The other advantage to Tinkercad is, the FreeCAD is we can design sub-assemblies, and then we can put them into a drawing, and you can physically design your robot, all the parts, put them together, all the holes will line up, everything will be perfect, and then when you go manufacture the parts, everything will magically fit together, as though someone designed it like that, right? So that's FreeCAD, and we'll go through that here in a little bit, and I'll show you how that works. Then I included another program on your thumb drive called OpenSCAD. OpenSCAD. And the beautiful thing about OpenSCAD is it's very difficult to use if you're a newbie, to say that straight up, but the advantage to you is you don't really have to know how to use it. By that I mean, I'm not going to raise it. So what OpenSCAD does is it creates CAD parts, CAD design parts, and STL, 3D parts with code. So you write a program that has parameters, and then over in the parameter box, and I'll show you this in a minute because I gave you a couple of different scripts that I've written. For instance, one cool thing that people like to do with 3D prints and your robots is if you want something that you can take off your robot without a tool, you could take a hex nut or a hex bolt and put a knob on it, right? So you can have a knob with a hole in it and a hex end on the end, pull your hex nut or bolt through it, and you've got a inside of it. And so I gave you both programs, so really all you have to do is load up SCAD and load up the appropriate script, go over and put your parameters in, make it look like the knurling you want, and the size of the knob, and, you know, if you're arthritic and 90 years old, you might want a knob this big. If you're, you know, nimble and 16, you might want a knob this big, right? So you can do all that, and it'll embed, you can pull it's made, like, the whole inside of it is made with the appropriate, catches and stuff, so when you pull a bolt through there, it won't come off. The handle will be stuck on your bolt, right? Or on your nut. And then you just hit save, saves the STL, go over to your slicer, slice it and print it. And you get this beautiful,
So I think-
you get this beautiful knob.
So I think one of the examples on that same that is, so this is called a servo horn, okay, and this is a servo, and these things come in like a couple of different standard sizes, okay? And this one happens to be round, and but often they're arms, and sometimes they're one arm, and
Oh, I
sometimes
wrote
they're
that
two.
for last year's robot.
But wasn't it an SCAD?
Yeah, it was an SCAD.
Okay, so
I've
basically,
already
he's
done
got
that.
this cool little tool that says, ooh, I need a servo horn. Great, what model of servo are you going to?
Yep.
Picks that gives you all this gearing automatic. How many arms do you want it? 1, 2, you want it, you know, how many holes? And you just hit go, and it basically generates an STL file that you go.
Generates the part for you, all the, a mesh for that. And you just save it and send it through your wheel, and bada bing, you got a servo arm to whatever. You can make it an arm, you can make it a wheel, you can make it a
whatever.
four-way arm or a six-way arm, or however you wanna do it. So that's what OpenSCAD is. It's great. If you go out and find for instance, if you need to make gears, drawing gears in CAD sucks, straight up. Unless you're really good at it and you do it all the time. But there's an OpenSCAD script that you can run that'll let you design gears all day long, and they'll all mesh. You know, they'll all work together, right?
So is that a web-based one as well, web app?
No, this is not a web app. This is a piece of software you install on your machine,
Okay.
and it runs on Mac and
Is
Windows.
it free also?
It's free. Yep.
Okay.
But the SCAD files, the recipes.
Yeah,
for
the
like-
recipes for parts.
They're gonna be up on the web.
Yeah, they're gonna be on the web. If you go out and search, you'll be able to find thousands of them,
Okay.
that do what I'm talking about.
So you don't have to, so there's programming them, that's not us.
That's a whole different,
Okay,
that-
there's
that-
using them,
yeah.
that's
Yeah,
us.
I get it.
Programming, it's a whole different deal.
Yeah.
I'm not even gonna bore you with that, cause that's.
So I
That's a
mean,
whole different
theoretically,
skill
we
set.
would use all three, depending on what we're doing.
Right, cause
Yeah.
they're all generating STLs.
Yeah,
Yeah.
I'll tell you though, that once you start using free, and I'll tell you right now, so learning curves, let's talk about learning curves. Learning curve for this, pretty flat. You know how to load a script, click on it, bam. You can make your
Here's
parameters.
the parameters.
All you gotta do is fill in what you want it to look like, and it'll, by the way, when you change the parameters, it recreates the part so you can see what it looks like. You know, so there's no surprise. Flat learning curve here. Learning curve here, no, I'd say it's, you know, like this, right? A little bit of a learning curve, but once you figure out the Lego block system, you can pretty much design it. Can you design complicated parts? Probably not, but you can design rudimentary parts. FreeCAD, learning curve, like this. You are going to have to make yourself sit down and get beat up in the process of trying to learn FreeCAD. And it's like that with any CAD program, because you have to learn to think in 3D space. You have to learn to think about the relationships between the geometries that you're putting in your part. And then when you get down the road, you actually need to think about the part design and how it comes out on that printer, because that will determine whether the part is gonna be strong enough to do what you need it to do. I'll take a great example. McCluskey, his first introduction into 3D printed parts for robots, because he told me when I first met him that you couldn't put 3D printed parts on a robot because they would break. And so the first thing I did was print him a set of hex motor mounts that mounted motors upside down on the bottom of his chassis. And those ran pretty good, still do. So,
You can all go out and look at those, I have that one.
but the problem is if you print that motor mount standing up, very weak print. But if you print it laying down, very strong print, right? So it's all about where you put the layers, right? If you put the layers longitudinally on your part, it becomes stronger than if you're putting the grain of the part in a high stress thing. You don't wanna pull against that grain, right? You wanna pull
With the
opposite.
grain.
Right.
Well, pull it like a
And
rope.
You want it to be at a 90 degree to your grain. Does that make sense? So you gotta keep that in mind when you design parts for a 3D printer, right?
So like if you were making a platform for a chair, you would want it to print like this,
So-
not like this.
Yes,
Yeah, well,
yes. Or for instance, if you have a screw hole, a screw going through a part, you typically don't want the screw hole this way and you're printing it like this with the screw hole horizontal to your print bed. Right? Because anything you're pulling against that screw is pulling against the adhesion of your layer. And you're susceptible to failure. Not saying you can't do that, cause you're gonna see lots of parts, cause the more complicated the parts get, then you have to weigh in, which part of this needs to be stronger as opposed to not so strong, right? And so, that all comes into play, right? But, and then you can combat some of those weaknesses in gusseting, in filleting, and some other things. And by the way, that's where Tinkercad just drops the ball. Putting gusseting or filleting into a part with Tinkercad, you will spend your whole lifetime doing that. I'm not saying you can't do it, because I've done it before, but it is not fun. Not fun at all.
And it's fun in FreeCAD.
FreeCAD,
Radius is,
easy.
here, add radius, click.
Click, boom, got gusseting all over the place, or radius everything, or put a chamfer on things. So, much more versatile, you'll get much more accurate prints, and you can print your designs out with pages that go into your engineering notebook, and it makes you look like you actually know what you're doing. With all the measurements and, like an engineering drawing would actually look. And like I said, my next door neighbor, what he does is he designs ductwork for industry, right, for AC systems. They use FreeCAD to do that. There's a whole mess of subculture FreeCAD, one of the big, surging things in FreeCAD right now is cabinet makers use it, because there's a workbench, and I'll explain the whole workbench industry to you later. But there's a workbench that says, I can go in here and I can say, I'm gonna design a desk with 3/4 inch plywood, and then when I put a plane in there, it makes it 3/4 inch plywood, right? So if I put a T-slot in it, it knows that I can't go more than 3/4 of an inch, or it'll cut the board in half, right? Or if I do put a slot in there and I'm gonna put another piece of plywood in it, it has to be 3/4 of an inch. It's got all those kinds of things built into it, so it makes designing furniture really easy, or cabinets that really easy, because all the offsets and everything are already made, right? So,
The classic granddaddy of these is AutoCAD,
yeah, okay,
which is kinda in between the two, cause it kind of mimic more of the T-square and the,
yeah. AutoCAD's kind of losing traction, which is why, they bought Fusion 360 was to compete, right? So anyway, parametric design, the learning curve, super steep. Over the summer, you're gonna have to spend more than several hours to learn that product. I'm just telling you. And plus, it can tell you
yeah, here,
the woes of learning.
here, let me show you.
The woes of learning FreeCAD.
That is where I am at.
But I will tell you, the reward for learning it is huge.
Yeah.
It really is. 'Cause-
And so if our kids learn that, they can go get a job.
Yeah, you can.
I mean, they really,
Yeah.
I can work a parametric CAD program where you throw me apart, let me CAD it, and I will show you that I am a hireable asset.
And so then the other thing you can do in FreeCAD that you can't do in Tinkercad is you can make sub-assemblies, so you can
Have parts on the
you
shelf.
can design a part, and then you can bolt it to another part, right? And if you design the parts right, you can actually animate it so that, you've seen the little animations where it shows the screw turning into the hole. You can do that in FreeCAD.
that's cool.
Now, you're gonna have to level up to do that, but you can do that, right? That is possible. So anyway, so we design the part here, and then we're gonna, and that part is gonna be in a format that is not printable. So, these are gonna give us a 3D model, if you will, and we have, so, with FreeCAD and Tinkercad, you can take that model and you can push it out to whichever way you're gonna do it. So, by that I mean, in this class, we're gonna 3D print, but you may at some point get to the point where you're gonna want to cut these on a CNC machine, right? And so, either TinkerCAD and FreeCAD can put out a file that is CNCable, if you wanna call it that. So, but we won't talk about the workflow for CNC, because that's completely different animal. So we're gonna, out of TinkerCAD, FreeCAD, OpenSCAD, we're gonna get a file called an STL. And that is a mesh format, so, think of,
A lot of triangles.
think of a mesh as a whole bunch of triangles. Now, I will say that, you wanna write this down, cause I can't include that on there, but there is one piece of Autodesk software that will save you, because, if you make a really complicated part in TinkerCAD, I have never had it happen in FreeCAD, but I suspect that you could make it happen, where you create a mesh that has a defect in it. And you'll see that defect in your slicer. So when you pull a mesh in, if it has a defect, you'll see you can go over to the preview of your mesh and you can see it, how it's going to slice it layer by layer. And if you see the final layer and you see holes in your print, you're going, wait, I didn't design a hole there or a layer missing. It's because your mesh has a defect in it. And you
What's
gotta-
the mesh?
So the mesh is the thing that defines your 3D part,
Okay.
okay? You can fix those meshes. The easiest way to fix a mesh is with a product called NetFab. As educators, you can get it for free. It does not work in the cloud, so you can install it on your local machine. You'll have to have an account with AutoCAD or Autodesk, but NetFab is how you fix a corrupted mesh file. Some of the files you download off the web, they'll be corrupted, and so you'll have to fix them before you get it ready for print. So, NetFab, you can bring in that defective mesh, and you just say, it'll tell you, this mesh has a problem, you want me to fix it? Say yes, it will fix your mesh, then resave it. You don't even have to know how to use NetFab. NetFab does a whole bunch of other stuff, we won't get into it there, because, again, that learning curve, that's super high. But, so anyway, so we're gonna get this STL, we're gonna assume that our STL is golden, beautiful, works, things are awesome. So then we're gonna take it to our next program, which is a slicer. So from the STL, we're gonna come to a slicer program. Okay? That is the slicer that I put on your thumb drive. It's a free product. It is one of the de facto standards in 3D printing, in the 3D printing world. It has the ability to hold different profiles for different printers, so if y'all have different 3D printers, even if they're the same model, they're gonna act differently, and you're gonna have to have a profile for each printer. So, Slicer will allow you to do that. Slicer will allow you to, as you get filament, believe it or not, you get PLA plus, black PLA plus prints different than red PLA plus, and it prints different than orange PLA plus, because the dyes in it cause it to have different liquidity properties and other things. So your temperatures may need to be a little bit different for each filament. So it allows you to have profiles for your printers, profiles for filament, and also a profile for a print. So each print, so in other words, I might have a print that might require some extraneous things printed so that the print comes out. It might have an overhang that I need to support, so that print will have supports, and I turn supports on for that print. But for another print, I don't want supports, right? Because I'm putting holes in it, but I know my printer will print those holes without a support in the middle of it. So I don't wanna have to do that cleanup, you know? So anyway, so we're gonna take our STL, we're gonna feed it into Slicer, we're gonna pick our printer, our filament, and we're gonna tell it to slice our print. And the outcome of Slicer is G-code. So you're gonna get a file that is a G-code file.
Which is specific to the printer.
The printer.
The commands for, so in other words, there's other 3D printers that have different commands with it.
So
we're
you
going to translate.
can't take G-code that you do for your Ender 5 Plus number 1, take it home and print it on your, your Ender 3. It might work some okay, but probably not gonna print as good as it does on the Ender 5, right? So your better bet, if you got something like that you wanna print at home or a friend or something like that, you can give them the STL, let them slice it for their printer. right? So then once it's sliced, we get the G code, and then we take the G code and we have to send it to the printer. Today the method is, we're gonna put it onto an SD card, put the SD card in the printer, select it off the SD card, let the printer print it. The tricky part about that is on these printers, preheating and stuff is kind of sketchy from the control panel, only because you can tell it's a preheat, but it likes to only preheat until it hits the temperature, and then it likes to start printing, right? And sometimes on a big print, that print bed is so big, when it reaches temp, it's only reached temp at the middle of the print bed. You might need to have it preheat for 10, 15, 20 minutes for the whole print bed to get hot enough.
And it's
hold
gonna
the big
soak up
print.
through the glass, cause it's measuring on the aluminum.
Right? So one of the ways we defeat that is we take from Slicer, we're gonna, and I'll put the image for this on your thumb drive as well, product called Octopi. And Octopi is a off-board print management system. And so what you'll do is you'll slice it, and in Slicer, you'll set your slicer up to actually send your print to the printer, the Octopi instance that's servicing that printer, and then Octopi will send the print to your printer. Okay? So in that case, you're gonna send your print to Octopi, and the beautiful thing about that is then Octopi stores it, and then if you need another one, you don't have to resend it to the printer, you just go to your Octopi, tell it to print another copy, right? Octopi also has the ability to select a design that you've already uploaded to it and tell it to preheat, and then you can see a graph of the preheat, and you can see how long it's been at temperature. You can also see how another important thing with 3D printers is that they stay at temperature at a very consistent level. And if you see like a bunch of wavy lines in your temperature, then you know we need to go back and reset the PIDs in the printer, so that you can go back and tune the PIDs so that you stay at temp much closer. You don't want that temperature to vary more than about half a degree while it's printing, right? So you can see all that in Octopi. There's tools in there to let you see all of that about your printing. It'll tell you estimated time of print completion. When you click on the design, it'll tell you how long it thinks it's gonna print. It's pretty accurate. You know, it might be plus or minus a few minutes, but on a 14-hour print, it's gonna be pretty darn close to 14 hours. So you go to Octopi, then Octopi will send it to your printer, and you control the printer with Octopi. The other beautiful thing about that is you're not sneaker netting SD cards all over the place, right? And they get corrupted from the going in and out of drives and things.
And the problem with these printers is using the micro SD cards, which are.
Yeah, and they're stuck way down in there,
They're
really hard to get back
They're
out.
tough to get in there, I mean, we need to buy some tweezers.
Yeah, it's a real pain in the butt. So Octopi is the way to go. And then of course you can put your printer someplace, and you can print, wherever in the file. Right? As long as somebody can see it, in the network, then they can print it. Right?
We got a network of printers.
You have to network the Octopi, and they have ways to do that. Yeah.
You gotta talk, because LISD does not want to put Raspberry Pi.
Yeah, they are not 3D printer friendly. But this is the preferred method. No two ways about it. We'll show you how that works later on. So that's the fundamental print flow, right? CAD, the STL, the slicer, the G-code, printing.
So, from a teacher point of view, okay, probably where you're gonna start out is, they send you their STL files. You email them, or something like that. Sometimes I even, you can have them send a link from Tinkercad, okay, so they can share a link in Tinkercad, and then I slice it from there, so I'm running the slicer on my Mac, okay, and they don't have to have the slicer. We've got code on there for them to slice, okay, so they can see